All right, guys, got another question on a video solution. This looks like a little bit of Stefan's law and energy transferred by radiation. So let me begin by putting Stefan's law here, and says that the energy transferred, or the rate of energy transferred, depends on these four factors. Stefan's constant, the emissivity of it, the area, and the temperature to the fourth power. So this one says, calculate the surface temperature of the sun, given that it is a sphere of 7 times 10 to the 8th, and it radiates this big power. So I'm just going to use these numbers. So this is 3.80 times 10 to the 26th watts. And Stefan's constant is that 5.67 times 10 to the negative 8. And the units are in joules per second in the top, and then divided by meters squared over Kelvin to the fourth power. This is a perfect radiator, so they want us to take the emissivity of it, emissivity of it as a 1. And the area is going to be a 4 pi r squared, because they say it's a sphere, and they give us this radius. I'll put meters and square it. And then we have temperature to the fourth power. So if we kind of analyze the units here, you're going to see that the square meters cancel off, and the watts, which is the same as a joule per second, cancel off, and this Kelvin to a fourth power is the only remaining unit. And that's perfect because it's going to have temperature to a fourth power. And so when we take the fourth root of it, we're going to get just Kelvin for the units. Now, in terms of numbers, let's take this 3.8 times 10 to the 26th. Let's divide it by 4.67 times 10 to the negative 8. I guess let's also divide that by a 4, and also divide it by a pi, and also divide it by 7 times 10 to the 8th squared. Okay, so that should be the temperature to the fourth power. Now let's take a fourth root, which I'm going to then raise it to 1/4, which is 0.25, and I get a surface temperature of 5,743 Kelvin. So there's our surface temperature of our sun based upon the power output. So there's A, and a good example of Stefan's law. Then it says, how much power does the sun radiate per square meter from its surface? This is referred to as intensity. So I'll just maybe put I for the intensity, but it's power per 1 square meter. And so the units would be the watts in 1 square meter. And so just coming back to our numbers, this is 3.80 times 10 to the 26. That's the total power coming from the sun. And it is spread out over the surface, which is 4 pi, and then 7 times 10 to the 8th meters squared. So again, this is the intensity. So 3.8 times 10 to the 26, then divided by a 4, divided by a pi, divided by a 7 times 10 to the 8th squared. And so the intensity is 6.17 times 10 to the 1, 2, 3, 4, 5, 6, 7 watts in 1 square meter. And that is a huge intensity. And that is, how much area, how much power is in just 1 square meter. And that's 61, close to 62 million watts of power in 1 square meter. So, of course, not a surprise. It's really big. Now, fortunately, that is not the amount of energy that eventually gets to us. Because C says, how much power in watts per square meter is the value by the time it gets to the Earth? And maybe that's worth drawing a picture first. And so if you have the sun and you draw kind of like a shell around the sun, you're saying at the surface there's this much power in 1 square meter. But as that energy flows outward, you can see that that total energy, or that power, because of conservation of energy, remains the same, but it is now spread out over a bigger area. And so that means the intensity has gone down. So using this information, we could say that this little shell that started on the surface of the sun as it spreads out is still the same rate of power. That's the principle of conservation of energy. So we still have this 3.80 times 10 to the 26 watts coming from the sun. It is just now spread out over a much bigger area by the time it gets all the way out to the Earth. And fortunately, they even say that the Earth is 1.5 times 10 to the 11th meters away. Okay. And so by the time it gets to us, planet Earth, what we often refer to as the solar constant, it would be something like this. 3.8 times 10 to the 26 divided by a 4 divided by a pi and divided by 1.5 times 10 to the 11th squared. And so very famous 1300, actually this is 1344, watts per square meter is considered the intensity of the upper atmosphere. This is what's coming in to the upper atmosphere. And after going through the entire atmosphere, it's been reduced. And so in general, we like to say on the surface of the Earth, we get about 1,000 watts per square meter. And so if you're going to put up some solar panel, this is the total rate per square meter you'll get. Of course, you're not going to be able to convert all of this to electrical energy, but, let's say you've got a 40% efficiency. You put up 1 square meter, you'll get about 400 watts out of that. I should measure my system because I'm a 5,000 watt system. And I got a lot more than 1 square meter, of course, because again, the efficiency is going to come into play. And so just without any efficiency, we would expect about 5 square meters. I got the minimum I can get. And my efficiency of mine, kind of an old system, I would guess is 25%. So let me take it and multiply by 4. So if I got 5 times 4, about 20 square meters, it's a pretty good size system. It takes up my entire roof here. It's one of the bigger ones I've seen. But I like it. I like it a lot. But that's a side note here. But that would be then the energy down on the, and again, the upper atmosphere, I think, is what they want. Okay. I think that was it. Was there a D? No, looks like that's it. All right, take care.